All right, welcome everyone. So today, just a reminder, so we're into week 5, and this week we have our second recitation exam in your scheduled recitation time. So, just something to keep in mind. We do have the follow-up exam questions as well, so they're kind of all together. You'll see the new material questions, you'll see the follow-up questions from exam 1, all in the same exam file. So you'll just do all of the problems that you need to. Keep in mind that when you're doing the follow-up exam 1 questions, you only need to redo the problems that you scored progressing on the first time. So if you got them all correct, you don't have to do any of those. If you only scored progressing on one of them, then that's the question you'll need to redo for on this exam. So you can look on UB Learns, you can look at, I have a kind of a sample layout document so you can see how what the exam will look like, how it will be laid out ahead of time. So there's no surprises when you sit down to actually answer the questions. All right, so today we're going to be looking at learning outcome D2 and D3. And so we're continuing on with the theme of derivative rules. So these rules that let us calculate derivatives a little bit quicker than if we were using, and a little bit easier than if we were using limits. So in D2, we're going to see the product and the quotient rule. So we're going to see how to compute derivatives of the product or the quotient of two functions. And then in D3, we won't finish that today, but we're going to start talking about the chain rule. All right, so let's get into it. And we're going to start with the product rule. So this is a derivative rule, and what it tells us is it tells us what to do if we have the product of two functions. So very well named. So in our little example here, we have f of x times s of x. And there's really like a multiplication there in the middle. So we have two functions, a first function f, a second function s. We're multiplying them together. And the question is, how do we differentiate that product? And the answer is with the product rule. So what does it say? We have the derivative of f times s. That's what we're interested in calculating. And what the product rule says is that it's equal to the derivative of f times function s plus function f times the derivative of s. So you can remember the formula, but I tend to remember it more of like a process. So let's see how maybe we can actually implement this product rule. So let's say we have a product of two functions, f of x times s, and we want to differentiate it. How do we actually implement this product rule? Well, one way to think of this is we just write down our product, two copies of our product. So function f times function s, and then we write down a second copy, function f times function s, and then we put a plus sign in between. So we put a plus sign in the middle there. And then in the first copy, we differentiate the first function. And then in the second copy, we apply the derivative to the second function. And that's kind of how we're going to implement the product rule in practice. So we write down two copies of our product, put a plus sign in the middle, and then in the first copy, apply the derivative to the first function, and then in the second copy, apply the derivative to the second function. And we'll see that in a few examples. But we just want to make a special note here. We've seen a couple other derivative rules, and one in particular was the sum rule. And what this did is it told us how to differentiate what happens when we have a function f plus a function s. So we had two functions that we were adding together, and what the sum rule said is their derivative is equal to, well, we just went term by term. So we applied the derivative to the first function, applied the derivative to the second function, and then just added the results. So that was what happens, well, we saw what happened before if we had addition. And we also called this term by term differentiation. It's another name that we sometimes use. So you might be thinking product rule would work something similar to that. If we have the product of two functions, if we have the product of two functions f times s, and we wanted to look at the derivative of that product, well, it seems very plausible that it would just be the first function times the second function, and you would just apply the derivative to both of those. So that's a very kind of natural assumption. It worked for the sum rule. Why wouldn't it work for the product rule? Turns out it doesn't. So this is just something, it's very tempting, but just to be very careful of. But this is wrong. So when we see multiplication of x terms, we have to use this slightly more kind of unnatural looking formula, the product rule, that might not be what we expect. So this does not work out. We can't just multiply the result or differentiate the first term, differentiate the second term, and just keep the multiplication sign in the middle there. All right, so let's see this in some examples. See how this works. So here we have the function 2x cubed minus 5x times 3x plus 1. And what we see here is that we have some x terms here. We have some other x terms over here. And then right in the middle, even though we don't normally write it, there's a multiplication sign. So right in the middle there, we have some multiplication going on. So we have some x terms times some other x terms, and we want to differentiate this. So this is a product of two functions. There's x terms on the left, x terms on the right, and then multiplication there in the middle. All right, so let's see how the product rule works. We want to calculate y prime. And so what we're going to do, we're going to apply the product rule here. So we're going to write down our product, 2 copies of it. So we'll write down 1 copy of our product, basically as is. We'll write down a second copy, 2x cubed minus 5x times 3x plus 1. And then we put a plus sign in the middle. And then in the first copy, we apply the derivative to the first function. And then in the second copy, we apply the derivative to the second function. And that's product rule. So this is where we do the product rule. And then from the rest of it is just differentiating those terms in the brackets. And we can do that like usual now. So just like we usually would. So we can differentiate that 2x cubed minus 5x. Just differentiate that like we normally would for a polynomial. Differentiate the 3x plus 1 just like we normally would. And then we're done. So let's see what we get. So derivative of 2x cubed, we apply the power rule, and we would get 6x squared. Then the derivative of minus 5x is just minus 5. So that's the derivative of the first term there. And then the 3x plus 1 that's outside of the brackets just stays there untouched. So it just stays as 3x plus 1. Then we have our plus sign in the middle. Then we have the 2x cubed minus 5x that was outside of the bracket, so that just sticks around. And then we differentiate 3x plus 1. So derivative of 3x is 3, and derivative of the plus 1 is 0. And that's it. We're done. So we have the derivative. And if needed, we could simplify, but we're not going to. So right now we're just worried about getting the derivative. Later on, we'll be interested in actually simplifying this. Maybe we want to figure out, where this derivative is equal to 0. So there it would be helpful to simplify. But for right now, we're just worried about getting the derivative. So once we're done calculating all the derivatives, we can just stop. All right, let's try another one. Another product rule one. So we have this function h of t equal to the square root of t times 5t plus 2. And again, we're looking at this, and what do we see? We see some variable terms on the left. We see some variable terms on the right. And then right there in the middle, even though we don't normally include that sign, there's multiplication. It's understood. There's some multiplication going on here. So we have the product of two functions. Square root function on the left times 5t plus 2 on the right. And we're going to just kind of remember when we have a square root function, it's going to be helpful to rewrite that as 1 over n. So the nth root we would write as 1 over n. So in our case, square root we would write as 1/2. And that's going to make differentiating a little bit easier. And we're going to do this one two ways. So the first way we're going to do it is with the product rule. After all, we have the product of two functions, so the product rule will work. So we're going to calculate h prime of t. And so how do we implement the product rule? We'll just write down two copies of your product. Square root t, and you know what? I said it and I forgot about it. Let's rewrite that as t to the 1/2. So we're going to write down two copies of our product. T to the 1/2 times 5t plus 2. Then we'll write down a second copy, t to the 1/2 times 5t plus 2. We put a plus sign in the middle there of our two copies. In the first copy, we apply the derivative to the first function. In the second copy, we apply the derivative to the second function. And that's the product rule. All right. So we've implemented our product rule. Now we just need to keep going and differentiate the terms inside the brackets. So the derivative of t to the 1/2 is 1/2, just doing power rule. So we bring down the exponent, 1/2, keep our variable the same, t. And then if we subtract 1 in the exponent, we get negative 1/2. So that's our derivative of the first term. And then the 5t plus 2, that's outside of the brackets, we just leave that alone, so it just stays as is. Then we have our plus sign. Then we have our t to the 1/2, that's outside of the brackets, so that just stays as is. And then we do the derivative of 5t plus 2. So derivative of 5t is 5, and then the derivative of the plus 2 is 0. So all told here, for our derivative h prime of t, we get that it's equal to 1/2 times t to the negative 1/2 times 5t plus 2 plus t to the 1/2 times 5. So that's our derivative using the product rule. Now we could do option 2, and what option 2 is, it's going to allow us to kind of bypass the product rule. And what we're going to do is just do the multiplication first. So that's sometimes an option. If you have the product of two functions, maybe you can just multiply things out and simplify first, and then it'll make the derivative that much easier. So we're going to actually do the multiplication first. So let's write down our function h of t equal to t to the 1/2 times 5t plus 2. And we're going to, like I said, do the multiplication first. So we're going to take this t to the 1/2 and we're going to multiply it to the 5t, and then we're going to multiply it to the 2. So we're going to distribute it, doing the multiplication. So if we do that, we get 5t to the 3/2. So we add the exponents. And then we get 2 times t to the 1/2. So in case you don't see it, t to the 1/2 times t is equal to, really there's kind of a hidden exponent of 1 there. And this is really t to the 1/2 plus 1, which is t to the 3/2. So when we multiply power functions like that, we add the exponents. So that's distributing, doing the multiplication first. And now if we look at it, we have basically a sum. We have the sum of two power functions, and we can do that with what we learned last week without the product rule. So we can, to actually calculate the derivative now, we can just apply the derivative to the t terms in the first part there, apply the derivative to the t terms in the second part there, and now just do power rule. So we get 5, and then we bring down the exponent, which is 3/2, keep our variable the same t, subtract 1 in the exponent to get 1/2. Then we go on to our second term. The 2 in front just stays in front, and then we do the power rule again. So we bring down the 1/2, keep our variable the same, and then subtract 1 in the exponent to get negative 1/2. And if we want, we could simplify this a little bit. Multiply the 5 and the 3 together to get 15. So we would get 15 over 2 times t to the 1/2. And then multiply the 2 and the 1/2 together to get 1. So we just have plus t to the negative 1/2 there. And so if you notice, the result we got from using the product rule looks a bit different than the result we got just doing the multiplication first. But if you were to simplify, you could go back and forth between the two, and you'd actually see that they are equal. So sometimes it's a little bit easier if you do the multiplication first, and you get a result that kind of looks a little bit nicer in the end. So if you can, maybe try it out, see if you can do the multiplication. But as it turns out, there's functions that we can't really do it. So if it's a power function times a power function, maybe try doing the multiplication first. But in this example, we have x times e to the x, and our hand is forced here. We have to do the product rule. So let's see how this is going to look. So we want to actually calculate the second derivative, y double prime, for this function y equal x times e to the x. So again, it's not really written, but there's a multiplication sign right in the middle there. It's kind of understood. It's x times e to the x. And so to get the second derivative, we first need to get the first derivative. We have to calculate y double prime, or y prime first. And then once we have y prime, we'll take that result, differentiate it to get y double prime. So we're going to do two derivatives here. All right, let's try out y prime. So we have x times e to the x. It's a product, so we have to use product rule. So we write down our product, x times e to the x. Then we write down a second copy, x times e to the x. Put a plus sign right there in the middle. And then in the first part, In the first copy, we apply the derivative to the first function, and in the second copy, we apply the derivative to the second function. So that's product rule. That's where we've used the product rule here. Now, it's just basic derivatives. So derivative of x is just 1. And then the e to the x there, that's outside the brackets, just stays e to the x. Then we have plus, and then we have our x there that's outside of the brackets, so that just stays the same. And then if we go to our chart, we want to differentiate e to the x. This is one we should probably start memorizing, but it's very nice in that e to the x is its own derivative. So the derivative of e to the x is just e to the x. So it doesn't look like we did anything there, but we actually did. So derivative of e to the x is e to the x. And we're done differentiating, but it's going to be helpful to kind of simplify this a little bit. And what we can do is we can factor out an e to the x. So if we look at our result here, the first term has an e to the x and the second term has an e to the x. So we can factor that out. And so we can simplify this and write it as 1, we can write it as 1 plus x times e to the x. All right, so that's our first derivative, and we see that it's written as a product. So we have a multiplication sign right there in the middle. So when we go on to do the second derivative, we're just going to take that result, apply the product rule to it, and that'll give us our second derivative. So y double prime then? Let's write down one copy of our function that we're differentiating. Let's write down a second copy. Put a plus sign there in the middle. And then in the first copy, apply the derivative to the first function. And in the second copy, apply the derivative to the second function. And again, that's where we're using product rule here. And then we keep going, just differentiating the terms in the brackets. And these should hopefully be a little bit easier. So derivative of 1 plus x, derivative of 1 is 0, derivative of x is just 1. And then the e to the x, that's outside of the bracket, just stays the same. Then we have plus, and then we have our plus, then we have our 1 plus x, which is outside of the brackets. So that just stays the same. And then finally, we have to differentiate that e to the x. And it's not going to look like we're going to do anything, but we actually are. Derivative of e to the x is just e to the x. And so we're done differentiating. So that's y double prime there. But for just a little practice, let's simplify. And we can do the same thing. We can factor out an e to the x. So if we look, the first term has an e to the x. The second term here has an e to the x. So if we factor that out, what are we left with? Well, we have 1 plus x times e to the x. And then just simplifying, we get 2 plus x times e to the x. And so there's our second derivative. All right. So that's a little practice using the product rule with e to the x. Let's try it now with some trig and inverse trig functions. All right, so we have the chart there on the right side. Hopefully those are some of the derivatives we start memorizing, but we're going to include them for now just as we're practicing these things. So in this example, we're going to calculate the derivative of, in the first one here, we're going to do the derivative of x squared times cosine x. And again, as we look at that, it's an x term times another x term. It's a product. So when we go to actually do the derivative, since it's a product of x terms, we're going to write down 2 copies of that product. x squared times cosine x is our first copy, and then just write down a second copy, x squared times cosine x. Put a plus sign there in the middle. And then in the first copy, we apply the derivative to the first function. And in the second copy, we apply the derivative to the second function. That's product rule. And then from there, differentiating those terms in the brackets, those are just basic derivatives now. So we do power rule on the x squared, we get 2x. Then we have cosine x outside of the brackets, so that stays the same. Then we have plus x squared, that's outside of the brackets, so that stays the same. And then for the derivative of cosine, let's look it up, and we see that it's negative sine. So derivative of cosine is negative sine x. And that's it. We're done differentiating. So not too bad. Probably to keep things a little bit cleaner, it's easy to lose track of negatives. So as we do more and more of these, there's going to be negatives floating around. And so it's, instead of having it written as plus x squared times negative sine x, it's going to be helpful to rewrite this and put that negative there in the middle. So we'll rewrite this as 2x cosine x minus x squared times sine x. So that's where I would stop with that one. All right, let's try one with an inverse trig function. So we're going to differentiate the function g of x equal to 2x plus 1 times arctan of x. And when we look at this, we have 2x plus 1, we have arctan, and we're multiplying them together. So it's a product of two functions. There's x terms on one side, x terms on the other side. So we have to use product rule. So to get our derivative, we just write down two copies of our product, 2x plus 1 arctan of x, 2x plus 1 times arctan of x. Put a plus sign there right in the middle. And then in the first copy, we're going to differentiate the first part, the first term. And then in the second copy, we differentiate the second part. And that's our product rule. Derivative of 2x plus 1 is just 2. So that's a nice easy one. Arctan of x there is outside of the bracket, so it just stays as is. Then we have our plus sign in the middle. And the 2x plus 1, that's outside of the brackets. So that just stays 2x plus 1. And then we want to differentiate arctan of x. So we find the inverse tan or arctan function on our derivative chart and look up what the derivative is. In this case, 1 over 1 plus x squared. So we kind of use those inverse notation, the minus 1 there, and arc as so inverse tan and arctan are really the same gadget. So when we differentiate arctan of x, it's just 1 over 1 plus x squared. And then to kind of clean this up a little bit, again, that's fine. We could just stop there. But maybe to clean it up just a little bit, I would write it as 2 arctan of x plus, and then I would take the 2x plus 1 and put it in the numerator. So I would write that second piece as 2x plus 1 over 1 plus x squared. Again, not absolutely necessary, but it's nice to kind of clean things up as you go along. All right, so that's pretty good with the product rule. So related to product rule it's everyone's favorite. It's going to be the quotient rule. And so there's a formula for how to differentiate a quotient. So you can just memorize the formula. But we'll see how to implement it. And it'll kind of feel like the product rule a little bit. But what we apply this rule when we see a fraction, the quotient of two functions. So we have a top function f divided by a bottom function s. And we see a fraction where there's x terms on the top, x terms on the bottom. So that's really what you're looking for. You're looking for a fraction where there's variables on both the top and the bottom. All right, so what does the quotient rule say? It says the derivative of f divided by s is equal to, and it's going to be a mouthful here. So it's equal to the derivative of f times s minus f times the derivative of s all over the function s squared. All right, so let's see how to actually implement this rule. So let's say we had a quotient. We had function f divided by function s. And we wanted to apply the derivative to this fraction. What do? Well, it's going to feel very similar to our product rule. At least the numerator will. So what we do is we write our fraction as a product. So top times bottom in that order. Then we write down a second copy, top times bottom in that order. And then instead of putting a plus sign in the middle, we put a minus sign. And then in the first copy, we apply the derivative to the first function. And in the second copy, we apply the derivative to the second function. So the numerator there, it feels a lot like the product rule, except it's a minus instead of a plus. And then we draw a big fraction sign, and then we just square the denominator. So when you're looking at this, the numerator is similar to the product rule, but it's not exactly the same. So it's similar. The numerator is similar to the product rule, except we have a minus instead of a plus sign there. And you know, when we write out the copies of our product there, we write the top one first, and we write the bottom function second. All right, so that's our quotient rule. Also, just another kind of note here is that, and this should be more of a warning, is just like the product rule, the quotient rule is probably not what you would first guess. If you were told to differentiate a function divided by another function, you would probably guess that the derivative of f divided by s, if we were to differentiate that whole fraction, would be equal to the derivative of the top divided by the derivative of the bottom. And it turns out that that's wrong. So that's no good either. So what you would kind of at first glance expect is that the derivative of the fraction would be the derivative of the terms in the top divided by the derivative of the terms in the bottom. And unfortunately, it would be really nice if that was the case, but it's not true. So kind of like the product rule, it doesn't behave quite as expected. So we have this more involved formula for how to differentiate a quotient. Another way to kind of remember this, here's a kind of a little jingle for you. Sort of a little rhyme. So you can write it, you can think of it, sing it to yourself. Low D high minus, I'm going to run out of room, minus high D low. And then draw the big line and you square the low. So you can think of it as, you can also remember it that way. Low D high minus high D low. Draw the big line and you square the low. Another way to remember this formula. So whatever works, works. All right, let's try an example of applying this derivative, this quotient rule. So in the first one here, we're going to differentiate the function x squared plus x minus 2, all divided by x cubed minus 6. And what do we see? We see it's a fraction, so there's x terms on the top, there's x terms on the bottom. So it's, you know, we see this fraction sign right there in the middle. It's a fraction. So our hand is kind of forced. We have to use the quotient rule. All right, so let's see how that works. So we're going to calculate y prime. And to do that, we're going to start by writing our fraction. We're going to write it as a product. So top times bottom. Then we do a second copy, just like we would with the product rule. And then where it's different is we put a minus sign right there in the middle. And then we're going to apply the derivative in the first copy to our first function. And then in the second copy, we apply the derivative to the second function. And so that's all the numerator. And then we draw our big fraction sign, division, and then we just square the original denominator. So x cubed minus 6. And we almost never do anything. We never multiply that denominator out. So just leave this alone. Don't do anything with it. So don't actually square that out. Just leave it as x cubed minus 6, just squared. All right, so that's quotient rule. That's where we applied the quotient rule. Now all that's left is to just differentiate those terms in the brackets. So for our first piece there, derivative of x squared plus x minus 2 is just 2x plus 1. Then we have that term outside of the brackets, the x cubed minus 6, so that stays the same. Then we have minus, then we have x squared plus x minus 2 outside of the brackets, so that just stays the same. And then x cubed minus 6, derivative of that is just 3x squared. So that's our numerator. And all over our denominator squared, x cubed minus 6 squared. And again, don't do that multiplication in the denominator. Just leave that as x cubed minus 6 squared. Now we could simplify the numerator. So sometimes that is helpful. So that might be something we do. But for right now, we're just interested in just getting the derivative. So we'll stop there. All right, so let's try it again, but now for a trig function. So we have another fraction, secant x over 1 plus tan x, and it's a fraction. So we have to use the quotient rule, or we're going to, at least. So we're going to calculate f prime of x. So how do we implement the quotient rule? Well, write down the fraction as a product. So top times bottom. Top times bottom. And then very similar to what we would do with product rule, except just put a minus there in the middle. Apply the derivative to the first function in the first copy. Apply the derivative to the second function in the second copy. And then we draw our big fraction sign, and then we square the original denominator. So 1 plus tangent x all squared. All right, so that's quotient rule. We had a fraction, saw that it was x terms on the top, x terms on the bottom, and we applied the quotient rule. So now all that's left is to just differentiate those terms in the brackets. So for secant x, what's the derivative of secant x? It's secant times tan. Nope. Yep, and that's let me get rid of the parentheses there. So the derivative of secant x is secant times tangent. So that's the derivative of that first bracket. Then we have the 1 plus tan x that's outside of our bracket, minus, then we have our secant x, and then we differentiate the terms in that second bracket, the 1 plus tan x. So derivative of 1 is 0, and then derivative of tangent, we go to our chart, look it up, or we have it memorized, and derivative of tangent is secant squared. And then this is all over, we draw our big fraction sign, and this is all over 1 plus tangent x all squared. And again, don't do anything to the denominator, just leave it as 1 plus tangent x all squared. And we could simplify that. We could go further, clean up the numerator a little bit, but right now we're just practicing on just getting the derivative. So we applied the quotient rule, we differentiated those terms in the bracket, we'll just stop there. All right, let's see one with some log functions and exponential functions. So let's look at the function x squared divided by natural log x. So it's another fraction. So we're going to need our quotient rule. So we want to do the derivative of function g. Let's write down our fraction as a product, top times bottom. Write down a second copy, top times bottom. Put a minus sign there in the middle. And then in the first copy, apply the derivative to the first function. And in the second copy, apply the derivative to the second function. Draw the big fraction sign, and then just square the denominator. So it'll be natural log x all squared. So that's the quotient rule. That's where we apply the quotient rule. Now we just got to finish differentiating those terms in the brackets. So derivative of x squared is just 2x. And then we keep the natural log x there the same. And we have minus x squared. And then derivative of natural log x, in case we don't remember it, we can look it up. It's 1 over x. So derivative of natural log x is 1 over x. And then we have our big fraction, and then this is natural log x all squared in the denominator. All right, so a little practice there using natural log. And again, if we wanted to, we could simplify the numerator a little bit, but we'll kind of leave that as is. All right. Try another one. Just keep practicing this. So it just comes with practice. So we're going to differentiate the function v of t, where v is equal to the natural exponential function e of t divided by 1 plus t squared. So we see a fraction. There's variable terms on the top. There's variable terms on the bottom. So we have to use our quotient rule. So let's write down our fraction. We'll write it as a product. So top times bottom. Do a second copy, top times bottom. In the middle, we put a minus sign because we're doing quotient rule. And then in the first copy, we differentiate the first part. And in the second copy, we differentiate the second part. And then this is all over, and we square the original denominator. And we're not going to multiply that out at all. So we'll leave that as 1 plus t squared all squared. We're not going to do anything to that. All right, so then we keep going. we have to differentiate those terms in the brackets. We want the derivative, first we want the derivative of e raised to the power t. Go to our chart, and nice easy one to remember, derivative of e to the t is e raised to the power t. It's the same thing. So this will just be e to the power t. 1 plus t squared just stays put, minus, we have another exponential function outside the brackets, so that just stays as is. And then the derivative of that 1 plus t squared term is 2t. So derivative of 1 is 0, and then the derivative of t squared is 2t. And then all of this over the original denominator squared. 1 plus t squared squared. And for practice, let's simplify this one. So if we look, both of the terms in our numerator have an exponential. So we can actually factor out that exponential. So we'll put that in front. And then we're left, what are we left over with? Well, we're left over with a 1, a t squared, and a negative 2t. So all told, we're left with 1 minus 2t plus t squared all over our original denominator squared. So we were able to factor that just to simplify. Again, not absolutely necessary at this point. You know, for right now, we're really just interested in getting the derivative, but that might be helpful later on where we need to try to factor or try to simplify. All right. So that's good with practice for quotient rule. And just a few more examples. And these two examples, they're kind of, now that we have quotient rule, they might be a little tricky because you see a fraction in both of them, but in both cases here, quotient rule is not necessary. You could do it, but it's not necessary. So in the first one, if we look at this, we do have a fraction, but no x term in the top. So the quotient rule is not really needed. So what can we do instead? Well, we've seen these before. Last week, when we first started looking at our derivative rules, the technique for dealing with this is just to use a negative exponent. So we could rewrite this instead as negative 5 times x raised to the negative 4. So we could rewrite with a negative exponent. So instead of division by x to the power 4, we could write it as multiplication by x to the power negative 4. And so now it just becomes a power rule question. So to get the derivative, we just apply the derivative to our variable part, to that x to the negative 4. And that's just power rule. So negative 5 is a constant in front, so that just stays in front. The negative 4 we bring down, keep our variable the same, and then we subtract 1 in the exponent to get negative 5. And then if we simplify, we get 20 times x to the minus 5. We multiply the negative 5 with the negative 4 to get 20. And that's it. We're done differentiating, and we didn't have to use the quotient rule because we were able to rewrite that fraction using negative exponents. All right, so let's see what happens in that second one. The 3x squared plus 2 square root x divided by x. And there we do have a fraction. We do see x terms on the top and the bottom. Sometimes we get lucky, like we're going to see in this one, and we can actually do the division first. This doesn't happen too often, but when it does, might as well make use of it so you don't have to do the quotient rule. And what we're going to do is we're going to break this fraction up into two separate fractions. So we're going to take the 3x squared, put that over our denominator, which is just x. Take the other term in the numerator, the 2 square root x, and put that over our entire denominator, which is just x. And because there's a plus sign in the numerator, we add these two fractions together. So a way to rewrite that function is to rewrite it as 3x squared over the denominator plus 2 square root x over the denominator. And then we keep simplifying. So we know with square roots, it's usually helpful to write that as x to the 1/2. And then from there, we can cancel or subtract exponents, however we want to think about it. So the 3x squared over x simplifies to just 3x. And then the second term there, really think of it as like an x to the power 1. So when we have division of power functions, we subtract the exponents. So this would be like 2 times x to the negative 1/2. So when you're dividing power functions, you can simplify by just subtracting the exponents. So 1/2 minus 1 is negative 1/2. So far, we've just rewritten our function. We did the division, so we split up our fraction, we simplified, and now what we have are just two power functions added together, so we can just do our basic derivative rules to get f prime. So our function was 3x plus 2x to the negative 1/2. And we're going to apply the derivative to the variable part in each of those. And then it's just basic power rule. So derivative of 3x is just 3. And then derivative of the x to the negative 1/2, bring down the negative 1/2, keep x the same, and then subtract 1 in the exponent to get negative 3/2. And then if we simplify, can do a little bit of simplifying there. The 2 times the negative 1/2 just gives us negative 1. So we end up with 3 minus x raised to the negative 3/2 power. And there's our derivative. And we didn't have to use quotient rule. We just did the division first. All right. So we'll stop there for product rule and quotient rule. And so now we can differentiate the product of two functions and the quotient of two functions. And what we're going to see in the next learning outcome is one other way to combine two functions. So we're going to see how to do the derivative of composite functions. And this is going to be chain rule. So first, let's talk about this way of combining two functions. So far, what have we seen? We've seen we can add functions, we could subtract two functions, we can multiply, and we can divide. Now there's really one other way to combine two functions, and it's by taking one function and plugging it into a second function. And we call that process composition. So we say a function h is the composition of functions f and u if h of x is equal to function f with u of x plugged in. And so some of the terminology we're going to use here for composition is we consider f to be the outer function. And we consider this u of x that's inside the parentheses there, we consider u of x to be the inner function. And when we think about composition, we can think of it like an assembly line. So we have some input x. And what happens on our assembly line here? Well, it first goes to our inner function. So it goes to our inner function u. And then what does function u do? It spits out u of x. So that's the result from our inner function. And then we take that result and we plug it into our outer function. So our outer function is f. So we take that number and we plug it into that next function f, and then that gives us our final output, which is f of u of x. So think of it like an assembly line. We start with number x. It goes into our inner function. That changes it, gives us u of x. Then we take that result, plug that into function f, our outer function. That does something to it. And then the final result is the output. It's f of u of x. And so really we can think of this assembly line, even though there's a bunch of like sub-processes here, we could really think of it as just collectively what we're doing is we're taking some input, and we could kind of think of all of this action with the inner function and the outer function here. We could really think of this as just one big process, which we would call h. So we take our input x, it goes into this whole routine of all those subroutines, and then it spits out, what does it spit out? H of x. So we can think of composition as sort of this assembly line where we're moving the input through function after function after function. So let's see how this works. In this example, we're going to just calculate a few different composite functions. So we're given the function f of x equal to secant x, and then we're given some other function u of x equal to x cubed. And so for part one, we're going to calculate the composite function f of u of x. So let's see how this looks. We're going to do f of u of x. That's really, let me give a little more room here. So we're going to do f of u of x. And what is u of x? Let's actually fill what u of x is. It's x cubed. So what we're going to do is we're going to take that x cubed and plug it into function f. So let's see how that looks. F of x, what was it? It was secant x. And in this, wherever we see an x term, what we're going to do is we're going to replace that x term with an x cubed. So all the x terms that we see in our function, we're going to replace with an x cubed. So instead of secant x, we're going to change that x to an x cubed. So that'll give us secant of x cubed. And that's what we're doing. So u of x was x cubed. We plugged that in. And then in our outer function, wherever we saw an x term, we changed that x to an x cubed. All right, let's try it the other way. Let's calculate the composite function u of f of x, see how that works out. So we're reversing the order here. So if you kind of think of it like an assembly line, if you start moving around the different processes of the assembly line, you would expect a different result. And that's what we're going to see, is we're going to get something different here. So let's fill in what f of x is. So f of x is our secant function. So we're just taking f of x and we're filling in what it actually is. And then the next step, if we think of u of x was equal to x cubed, what we're going to do is we're going to take wherever we see an x there, we're going to replace it with secant x. So instead of x cubed, we're going to change that x to a secant x, and we'll get secant x all cubed. And if we compare these are very different. So those two results are different. One is secant of x cubed, the other one is secant x all cubed. So kind of looks similar, but they are technically different. And so in the first example, function f was our outer function. It's the thing we do last. And then function u is our inner function. It's the thing we do first. It's inside our function. It's inside the parentheses. And we reversed it for part 2 here. F was our inner function and u was our outer function. All right, so let's do a little bit more practice with just composite functions. So here, in this example we had 2 different functions and then we combined them in a way to get one function. A lot of times we're going to have that one function and we want to be able to break it apart into kind of the 2 different pieces. And so that's what we're going to see in this example is we have few different functions here, and we want to write each of these functions as a composite of simpler functions. So we want to identify 2 simpler functions that would combine to give us this. And so we're gonna break these apart into an inner function and an outer function. And for each of these different ones, we want to identify what is the inner function, what is the outer function. And so the inner function is it's usually inside parentheses. That's why we call it the inner function. It's inside a set of parentheses usually. And then the outer function is just everything else. All right, so let's look at that first one. We want to break this apart into an inner function and an outer function. And sticking with the same kind of terminology, we're going to call our inner function u of x, and we're going to call our outer function f of x. So our inner function in this case is what's inside the parentheses. So if we look, this first function is x to the 4th plus 9x plus 3 inside parentheses, and then all raised to the power 8. So that x to the 4th plus 9x plus 3 is our inner function. It's inside the parentheses. And then f of x, our outer function, it's what happens last. It's outside of everything. It's everything else. And so it's that raised to the power 8 that we're seeing here, this exponent 8. So it's the power function raised to the power 8. And to give it a variable, we'll call it x raised to the power 8. So we've broken this function down into 2 simpler functions, an inner function and an outer function. Let's try it for the next one. So the next one, we have sine of x to the 4th plus 9x plus 3. We want to break this one apart into 2 simpler functions, an inner and an outer. Again, we see parentheses. So usually what our inner function is, it's those terms inside the parentheses. So we're going to let u of x in this case equal x to the fourth plus 9x plus 3. And then the outer function is everything else. And so everything else here is the sine. So f of x is going to be sine of whatever, and to give it a variable, we'll give it variable x. So it'll be sine of x. That's our outer function. Another one. E raised to the x to the fourth plus 9x plus 3. We want to break this one apart. And again, we're looking for a function that's inside of another function. And very similar, except we don't see the parentheses here, but they're kind of understood, is that the outer function is the exponential, and our inner function here is the exact same thing we've been seeing. It's this u of x equal to x to the fourth plus 9x plus 3. The inner is everything inside the exponent. And then our outer function, this is everything else. And so everything else is the exponential part. So it would be just e raised to whatever. And we want a variable there, so let's just put an x there. So it'll be e raised to the x. So we're breaking these functions apart into two simpler functions. Let's try one more, natural log. Natural log x to the fourth plus 9x plus 3. And there we see our parentheses again. So identify the term that's inside the parentheses. That's going to be our inner function. It's inside the parentheses. And that's, that one up here is a 3. And then everything else is our outer function. So the natural log here. That's going to be our outer function. It's outside. It's the last thing we do. So it'll be the natural log of whatever. And we want to give it a variable, so let's put an x in there. And so that's just another example of breaking apart a composite function into two simpler functions, an inner and an outer. All right, let's look at how we actually differentiate these. So we have all these composite functions. We've been playing some games with breaking them apart and combining them. Well, how do we actually differentiate these? And so as it stands, doing the composite of two functions is a very different process than just arithmetic, adding, subtracting, multiplying, dividing. This is a very different process. And so we have a different rule for how to calculate these derivatives. And we call it the chain rule. So let's read through it. Chain rule says, let u be a differentiable function, and let f be a differentiable function at u of x. Then the way we differentiate their composition, f of u of x, well, that derivative is equal to f prime evaluated at u of x times u prime of x. So really what the chain rule tells us, this is telling us how to differentiate composite functions. So when you see parentheses and then with x terms inside parentheses, chances are you might have to use chain rule. You have the composition of two functions. All right, and we think of this more like a process. So you can remember the formula, but it's probably a little easier to think of it like a process. So when we identify that we have a composition, how does the chain rule work? Well, first thing is we do the derivative of the outer function. So that's why we want to be able to identify what the outer function is, because we want to do the derivative of just that outer function. We'll get the derivative of our outer function, And then into that, we're going to plug just our inner function. So we're going to do the derivative of our outer function. We're going to take our old inner function, plug that into the f prime. And then finally, we're going to multiply that result by u prime. So we're going to do the derivative as sort of our third step. We're going to multiply by the derivative of just the inner function. So how we do the chain rule, we differentiate the outer function, we plug into that, we plug our inner function, and then we multiply by the derivative of the inner function. So it's going to be important to be able to identify what's the outer function, what's the inner function. So we're going to stop there for today. So we just get to it. So kind of teasing what we'll be doing next time on Thursday. And what we're going to see is we're going to look at a bunch of special cases. So there's going to be a general power rule, which tells us what happens if the power function is the outer function. We're going to look at general trig rules, and that's if our trig function is the outer function. Same thing for exponential. If we have an exponential outer function, there's sort of a special case for the chain rule in that case. And then same thing for log functions. So we're going to be looking at a few different special cases of the chain rule and just kind of get practice doing this chain rule differentiation. But that'll be for next time. All right, so we're going to stop there for today. And keep in mind, though, this week is recitation exam 2. So if you're in a Tuesday recitation, you have your exam today. If you have your Thursday recitation, you have your exam on Thursday. And, take a look at the course website. I have a list of the questions or, what topics are going to be covered on exam 2. You'll want to review your exam 1 solutions. And if you got marked as progressing, you'll be able to try those questions again on the exam, either today or tomorrow or on Thursday. So you'll be able to try those questions again for full credit. All right, so we're gonna stop there, and good luck studying. Feel free to let me know if you have any questions, and we'll see everyone on Thursday.